Hello and welcome to the 5th week of our course. In this week we will be studying the concept of connected spaces or connectedness. So what is the idea behind this concept? So idea is suppose that you have the real line, so x is the real line, and you take the open interval say 0 1 0 1 in R. Now suppose that you are standing near 0, so you are a stick figure standing near 0 and you want to walk to the other endpoint, which is 1. Now you can do this continuously without taking any jumps, right? So all these points are steps you can take without missing any point in this interval 0 to 1, and you will end up in the next end point, which is at 1. So you can travel without jumps, okay? So without missing any points in 0 1. So the other case is when you have, let us say, two open intervals 0 1 and let us say another open interval 3 by 2 to 2. So now if you are standing near 0 again, you're standing near 0 and you want to reach the other endpoint, which is at 2. Now you can travel continuously until 1, so you will reach the endpoint 1, but now there is a gap here, right? There is a gap and you have to jump. So you have to jump to get to the other open interval which starts at 3 by 2, and then you can travel to 2. So this is traveling with jumps. So this is the informal idea for connected spaces. Connectedness is precisely when you can travel without jumps. Travel without jumps gives you connected spaces, and traveling with jumps gives you disconnected spaces. So how can we formalize this idea in a mathematically more precise way? And let us give the definition for connectedness in this regard. So definition, so let X be a topological space, then a separation of X is a pair of open sets A and B in X, open non-empty. So let me add this here, open non-empty sets, non-empty. This is important actually. So open non-empty sets A and B in X such that A intersection B is empty, which is just saying that A and B are disjoint sets, and X is the union of these two sets A and B. So we say that AB is a separation of X. And now we can define a connected space. A connected space X is a topological space which has no separation. Okay, so which has no separation. So what does it mean for X to not have any separation? So notice that so this is a remark. So if AB is a separation of X, then you know A complement is equal to B, because X is the disjoint union of A and B, since A intersection B is empty and X is the union of these two sets. And similarly B complement equals A. And now this implies that both A and B are what are called clopin sets. So clopin sets means that they are both open and closed at the same time. Okay, so both A and B are open and both A and B are closed. Now notice that the empty set and X are both clopin. So when you have a separation of X, then you are getting clopin sets which are clopin sets other than the empty set and X. So equivalent definition of connectedness is that the only clopin subsets of X are phi and X. So how can we show this? So let's prove this. So in one direction we have already seen that if AB is a separation of X, then so if X is not connected, say, so if X is not connected, then this implies that AB is a separation of X, and then A and B are clopin subsets of X, and these are different from phi and X. So on the other hand, if X is connected and A is a clopin subset, then if you take U as A and V as a complement, then both U and V are open, right? Because A is open, so U is open, and A is closed, so V is open. So both U and V are open, and X is the union of these two sets, U and V, and U and V are disjoint, which means that UV is a separation of X, which contradicts that X is connected, which contradicts the assumption that X is connected. So the equivalent definition of connectedness is to say that the only clopin subsets of X are the empty set and the set itself. Here notice that both U and V are non-empty precisely when A is not equal to either phi or X. So if A is equal to either phi or X, then one of them has to be empty. Either U is empty or V is empty. And if you want both to be non-empty, then the only possibility is to exclude are the empty set and X itself, and this is also something that we have used in this proof. Okay, so now let us see what are some criteria for connectedness of a subspace. Now let us look at a lemma which gives us a condition for a subspace y of X to be connected. So first of all, a separation for y of y is a pair of subsets A and B of y which are non-empty open sets in y, meaning that A and B belong to tau y, so it is they are open in the subspace topology of y, and they follow the three properties as listed here. So first one is that A intersection B is empty, they are disjoint, their union is y, and the third one is that the closure of A intersection with B is empty, and the closure of A intersection B closure is also empty. So of course, if you have a separation of y, then the first two are automatic, and so this is by definition of a separation. On the other hand, the third one is the non-trivial part, and we have to prove this. So just a remark before we see the proof is that if y is equal to x, so if you take y to be x itself, then of course 1 and 2 are again satisfied. If you take a separation of x, then we have seen that they are A and B are open disjoint sets which are non-empty, and their union is x, so they are a separation. On the other hand, the third part is also automatically satisfied, so 3 is automatically satisfied since A closure intersection B is equal to A intersection B. Since A is closed, we have A closure equals A, and this is an empty set. So the third part is automatically satisfied if you take y to be x, but if y is in general subspace of x other than x itself, then we need to show that the third part is satisfied for a separation of y. And the last part is simply saying that y is connected, the subspace y is connected in the subspace topology if there is no separation of y. So this is of course by definition of connectedness. So we just have to check that if you take a separation, then the third part of this of the property is satisfied. So let us see a proof of this third part. So now let A be a separation of y. So of course we have A, B belong to tau y. They are open sets. A and B are non-empty, and A intersection B is the empty set. They are disjoint sets, and finally y equals A union B. So now to show that A closure intersection B is the empty set, we have that A is closed in y, right? Because the complement of A in y is just B, which is open in y. So A is closed in y, and this implies that A is equal to the closure of A in the subspace topology. Remember this notation from before, where we distinguished between the closure of a subset of a subspace within the subspace topology and with the topology of the larger space. So this is just saying that A is closed in y. On the other hand, we have proved that the closure of A in Y is nothing but the closure of A in X intersecting with Y. And now, so we have A equals, so this is A equals A closure intersection Y, and I claim that this is equivalent to A equals A closure intersection Y is equivalent to saying that A closure intersection B is empty. So for example, I'll just show the forward implication. So let us take the forward implication condition, which says that A is equal to A closure intersection Y, and now we just replace Y with the union A union B. This was the property for the separation here, and now this is nothing but A closure intersection A union A closure intersection B. But A is a subset of A closure, so A closure intersection A is just A, and union A closure intersection with B. So we have A is equal to A union A closure intersection B, and this implies that either A closure intersection B is a subset of A, or A closure intersection B is empty. But the first part is not possible since A intersection B is empty. So the only possibility is A closure intersection B is empty. And you can also show the other reverse implication, and I leave it to you as an exercise. So reverse implication is left as an exercise, which is essentially this same argument but in reverse. Okay, so this gives a characterization of subspaces which are connected in the subspace topology. Now let us look at another lemma which gives you a way to visualize connected subspaces in a disconnected space. So if Y is a connected subspace of X and X is not connected and it has a separation AB, then either Y is contained in A or Y is contained in B. So why is this the case? Let us see a proof. So suppose that neither Y is a subset of A nor Y is a subset of B. Then define U as A intersection Y and V as B intersection Y. So they are open in Y, both are open in Y because they both A and B are open in X, and these are the Y is given the subspace topology. So both A and B are open in Y. They are non-empty since neither Y is a subset of A nor Y is a subset of B. So meaning that even if one of them is satisfied, then if for example if Y is a subset of A, then V will be non-empty because X is equal to the union of A and B, and similarly if Y is a subset of B, then U will be empty. So if neither Y if neither conditions hold, Y is subset of A nor Y is subset of B, then both U and V are non-empty, they are open, and they are also disjoint since U intersection V is nothing but A intersection B intersection Y, and this is the empty set because A and B are disjoint. So this means that UV is a separation of Y, and this is a contradiction to the fact that y is connected. Contradiction to the fact that y is connected. And so this means that either y is a subset of A or y is a subset of B. And now let us look at some examples of connected and not connected subspaces. So the first example that we will consider is y to be the set -1 0 union 0 1. So note that this is open at the point 0 for both these parts, and this is given the subspace topology of R. And now if you let A to be -1 0 and B to be 0 1, then of course they are non-empty. A and B are both open, and B are open in the subspace topology of Y, because say A is nothing but -2 0 intersection Y, and similarly B is 0 2 intersection Y. So both A and B are open in Y, they are disjoint, and of course non-empty. So this means that AB is a separation of Y, and so Y is not connected. And now here notice that even though so what is A closure? A closure is nothing but -1 0, okay, included, 0 included. Similarly B closure is 0 included 1, and A closure intersection B is empty, B closure intersection A is empty, but A closure intersection B closure is precisely the point, the set 0, so this is non-empty. Okay, so A closure intersection B closure might be non-empty, and yet the set Y, the subspace Y, can have a separation. Okay, so we only want these two, but not the third one, not the intersection of both closures. For the second example, we can take y to be the rational numbers and x to be the real numbers, and as usual y is given the subspace topology here. And now if you let A to be the set Q intersection with the open interval -∞ to, let's say, √2, and B to be the intersection of Q with the interval √2 to infinity, then of course A and B are non-empty. These are non-empty, open in Y, and they are also disjoint. So A intersection B is empty set. This means that AB is a separation of Y, and so Q is not connected in R. And using similar methods you can prove that R minus Q is not connected either. So here notice that you can take any irrational R rather than taking √2. You can take any irrational number and it will still work. So a separation may not be unique. You can have many separations for the same set. Now let us look at another example. So take X to be R, and the topology tau is the finite complement topology on R. Finite complement topology. Now suppose that AB is a separation of R, then this means that a complement which is equal to B must be finite, because this is how we define open sets in the finite complement topology, so they were precisely the sets whose complement is finite. So since A is open, A complement, which is equal to B, must be finite, and similarly B complement, which is equal to A, must be finite. So since AB is a separation for R, this implies that R is a union of two finite sets, which is a contradiction because R is an infinite set, which is a contradiction since R is infinite, because union of two finite sets must be finite and R is infinite. Why is R infinite? Well, we can use one of the characterizations of infinite sets that we did in the first week, and here you have the inclusion of the natural numbers to the real numbers, and this is an injective map, and this implies that R is infinite. Actually, this is equivalent to saying that R is infinite. So we see that this means that there is no separation AB of R, and so R is connected in the finite complement topology. Now for yet another example, take X to be R with the lower limit topology. So tau L is the lower limit topology on R, but RL can be written as the union of two sets minus infinity to A union A closed at A to infinity for any real number A, and both these sets are open in the lower limit topology, as we know, and they are disjoint and of course non-empty. So this means that RL is not connected, and RL in fact is an example of what are called totally disconnected spaces, which are spaces in which the only connected subspaces are the singleton sets. So RL is a so-called totally disconnected space.